So in today's video, what we are going to do is look at non-homogeneous problems for heat equation. So non-homogeneous problem for heat equation. Heat equation, clear? So let us write it down. The problem which we are looking for is this, right? This is equals to F in Rn cross 0 infinity, okay, and U is essentially 0. We start with 0, okay, on Rn cross T equals to 0. So what is the problem here? The problem is, let us assume that, let me do it for one dimension. In one dimension, the problem looks like this, no? This is T, and that's, let's say that's your R. So in Rn is basically, in the base dimension here, and that's the time dimension. So what it is saying here in the case of one dimension is, in this part of the domain, okay, in this part of the domain, you are looking for a U such that F is given to you. So given F, okay, we are looking for an unknown U is unknown, okay, U is unknown. So we are looking for an unknown U such that ut minus Laplacian of U, if you remember, Laplacian of U is with respect to x, that is equals to F, okay. This is in this part, and U is equals to 0 on the line. So here U has to be 0. Here in R cross T equals to 0. In this line T equals to 0. So in this line this has to be 0. U has to be 0. Okay. And we want to, what we want to do, M, to produce a formula for a solution, clear? So we want to find a formula which will actually give us a solution. Yes. So let us start doing that. First thing first, see, if you, of course we will use our fundamental theorem, as you would have guessed till now. Let's say xt, yes, this map xt going to the fundamental solution of heat operator phi at the point x minus y t minus s. Okay, so essentially t is getting replaced to t minus s. Yeah, so this is a solution of ut minus Laplacian of u equals to 0, right? That's your solution for y in Rn and 0 less than, so s is between 0 and t. So what I'm trying to say is this: let us assume that you are working with a y which is in Rn. Okay, take an arbitrary point y in Rn and take s which lies between 0 and 2. Say, so s can be anything between 0 and t. Yeah, now you just look at what is phi at the point x minus y t minus s. Okay, this thing. Of course, what phi does, that phi is always a solution of ut minus Laplacian of u. It's a fundamental solution, right? So where capital phi is the fundamental solution, right? It's the fundamental solution of heat operator. See, since it is a fundamental solution, this solves the heat equation, right? And why does it do that? Let's see. You see, x minus y, for a given a x in Rn, y in Rn, x minus y is in Rn. Yes. So this is in Rn, and t minus s. See, s lies between 0 and t. So t minus s is always positive. Yeah, so phi of point in Rn times the time variable t, which is time variable which is which is positive, right? So essentially this particular function will solve the heat equation. Fine. That is why you need this condition. Okay, because otherwise t minus s can be negative. In that case, this is not. This will become 0. Okay, it solves, but it will become 0. Okay, so now, therefore, from our earlier discussions, we can say, we can just think of it like this: that for a fixed s, right? For a fixed s, if you write the function like this, okay, you write it like this: u of x t s, okay, xts. I will explain to you what I mean by this. This is given by integral over Rn phi of x minus y t minus s, okay, f of ys dy. Okay, so essentially what am I saying? Now for any fixed s, this kind of u, if you define u like this u must solve ut, okay, of course xt is there, s minus Laplacian of u s, this is equals to 0 in Rn cross s infinity, and u evaluated at xts is f of evaluated at the point s on Rn cross t equals to 0. Okay, so let me explain to you what I meant by this. See, essentially here, if you remember in Duhamel's principle, what did we do? If you remember in ODE, Duhamel's principle, what we did is we wanted to solve the inhomogeneous problem, and what did you do? We solved the inhomogeneous problem by solving a bunch of homogeneous problems, right? Yes. So here also we are doing exactly the same thing. We are solving a bunch of homogeneous. So sorry, one small detail thing which I moved. This has to be t equals to s. Clear? So what we did is essentially we solved this problem. Yeah. So we solved this problem. You see, this is at the level t equals to s. You see, I have to do it for 0 infinity. Yeah, I have to solve this equation equals to f, and the time variable is between 0 and infinity. Here what am I doing is I am solving the homogeneous problem, but what is the initial condition? If you remember your Duhamel's principle, the initial condition is f, but not at t equals to, we are not evaluating between 0 and infinity, but evaluating at a particular t equals to s. Now after that you run s between 0 and whatever. So here s is between 0 and infinity, that will give you the whole 0 infinity thing. So that is why u, which I am going to define, which I defined here, that I defined it between integral over Rn phi of x minus t t minus s f of ys dy. Okay, is this clear? See, what I am trying to say is this. If you recall, what did your Duhamel's principle do? Duhamel's principle said that if you want to solve a inhomogeneous problem, what you do is you solve a bunch of homogeneous problems, right? But with some initial condition. The initial condition is u. Here it becomes homogeneous problem, but here the initial condition changes to u is f, right? At some level t equals to s. Yeah, for some level s or tau. In our case it was tau, right? So here I am just writing it to be s. Okay, now what here it is doing is, this is a homogeneous problem with this initial condition, right? Okay, and I'm just writing down the solution like this, right? This is just the solution which we got from the earlier, we did it earlier, right? Yeah, this is what we found. Now here, what is this s? What does that say? You see, I am evaluating this problem for t equals to s, right? So that is why I am just writing s like this. So u also depends on s, that's all. Okay, so that is why this t minus s term is coming. So xt, this is just a variable that is always there, right? You do not have to do anything, but this s will represent that I am evaluating the problem, okay, at t equals to s. That's all, okay, or in between s infinity. Yeah. Now you see, if I am asking you just from your intuition that if I want to find a solution of 1, what do you think that will be? It should be that s will run between 0 and t, right? If s runs between 0 and t, that should be your solution, right? Okay, so that is what we'll do. Let's do that. So now, what does Duhamel's principle say? Duhamel's principle says, if you remember by OD, see, the thing is, you may ask that I didn't prove any Duhamel's principle for PD, then what am I using here? Yes, you do not have to prove. This is what I am doing. I am trying to prove Duhamel's principle for PDEs, okay? In ODE, the Duhamel's principle gives me that I can solve a bunch of homogeneous problem and use those solutions to construct a solution of a inhomogeneous problem, right? So here also I am going to do something similar. So what am I going to do? I am going to construct a problem like a solution like this. Let's say you solve the original inhomogeneous problem, and that is given by 0 to t u of x t s, okay, ds. So this x is in Rn and t greater than equal 0. Clear? So Duhamel's principle, from Duhamel's principle, what can I do? See, Duhamel's principle essentially says that I am evaluating this problem at t equals to s. Now if you just run this s, right, yeah, between 0 and t, so basically if you take the s to till 0 and after that integrate it in the whole time interval, then we should get the solution of this problem. Okay, this is what I am just doing it here. Okay, so essentially u of xt, I am allowing, yes, I am allowing my, I mean, this is t is an arbitrary t, yeah, this t is between 0 and infinity, that's all. Okay, so 0 and t u of xt s ds. So this integration is with respect to s, right? Okay, so here xt is fixed, this integration is with respect to s. Now, so if you rewrite it, so rewriting, what do we have? We have u of xt should look like this, 0 to t, okay, integral over Rn phi of x minus y t minus s f of y comma s dy ds. Again, please understand this one. How did we get it? So let me put it this way. How did we achieve this? Achieved this, okay? This is our guess, huh? This is our guess. We did not do anything. This is just a guess from the experience of PD, experience of ODE. That's what I'm saying. Yeah, this is just a guess. This see, Duhamel's principle. Whenever I'm saying Duhamel's principle says, it does not mean that it says this. Yeah, I mean, from you can actually use Duhamel's principle to say that it may UXT should look like this. Okay, so let me put it this way: should UXT should look like this. Yeah, I don't know if it will look like this. What I am trying to say is, from our experience of ODEs, we know that u of xt, if I want to really find what u of xt, it should look like that. That's what. Yeah. So what we have to do is we have to prove that, yeah, our proposition is actually indeed true. So what we want to do, let me write it properly. This essentially what it means is 0 to t, okay, 1 by if I write it, it is 4 pi t minus s whole power n by 2, okay, and integral over Rn e exponential minus x minus y square by t minus s square f of y s dy ds. Okay, this is for x in Rn and T positive. Clear? So what we have to do now, what is our aim? Our aim is to confirm that this is true. So let's say that that's your 1. Okay, so aim is to confirm that 1 actually solves this problem. Okay, this is 1, the problem is 1, so let's say 2. Okay, so 2 actually solves the 1. Okay, so this formula u of xt given by 2 actually solves 1. So we have to prove this. Yes, so we start with some assumption first. Assumption on f. Okay, assumption on f. So we'll assume f, of course it is twice differentiable with respect to x, once differentiable with respect to t in Rn cross 0 infinity. Okay, with compact support. Clear? With a compact support. So essentially, if you take the closure, so essentially what it says is f not equals to 0, this set, the set of all those x where f not equals to 0, if you take the closure of that thing, that is compact. Okay, that is what it says, right? Okay, so we are going to use this thing and to find out that this is indeed the solution. So let me write down the theorem first. So the theorem, so this is the existence theorem. Okay, it says that let u be given by 2 okay, then number 1, u is in C21 of Rn cross 0 infinity. Clear? Okay, so what it is saying is, if you are taking a f, okay, with a compact support and twice differentiable with respect to x variable, once differentiable with respect to t variable. Yes, if you are taking f like that, so if you remember what is the equation is ut minus Laplacian of u equals to f. Okay, if you are taking a f with a compact support and in C21, okay, if you are taking it like this, then what the equation says, the theorem says, is the u which you are going to get by 2. So this u which you are going to get, this u is C21 of Rn cross 0 infinity. So it is twice differentiable with respect to x variable, once differentiable with respect to t variable. Okay, moreover, ut of xt minus Laplacian of u xt, that is going to be equals to, if you have guessed it, it is going to be f of xt. Okay, this is x in Rn and t positive. Okay, why this is the case, ut of xt minus Laplacian of uxt equals to so this is the thing. See, we want, this is our hope, that the solution which we defined like this, yeah, so this basically 2, this should solve our original problem 1, right? Okay, so 2 must satisfy ut at every point, ut minus Laplacian u equals to f. Okay, that is what I am just writing. At every point this should satisfy this, yeah. And there is a boundary condition, if you remember. So how does it satisfy the boundary condition? It can satisfy like this. So limit, if you take any point xt, okay, xt, where are you going to take? From x in Rn, t positive. Okay, if you are taking any such point and that goes to x naught 0, okay, let's say x is in Rn and t positive, right? So if you take any such point, u of xt, that should be equals to 0. If you remember, see, the equation here is u is 0 on this boundary. So if you take any point on the boundary, let's say this is the point x naught 0, so and you take any sequence, okay, any sequence here, so that sequence must converge. If it converges to x naught 0, then u at that point, okay, those should converge to 0. This is what it is written here. Clear? Okay, so let's look at the proof of this thing and then we are done with this inhomogeneous problem. So first thing first, see, I mean, you have this phi, right? You have this phi. Sorry, you have this u. Now I can just take ut minus Laplacian of u. Yes, I can just calculate this thing and we are done with, right? But I can't do that, right? Because if I'm taking ut minus Laplacian of u, you see this problem has a singularity, right? This has a singularity at t equals to s, right? And this also has a singularity. Okay, so essentially, you see, this is a phi. This is capital phi, right? This capital phi that has a singularity at 0 0. So x equals to y and t equals to s. This has a singularity. Okay, so we cannot use I mean, differentiation under the sign of integration. Okay, that cannot be done. So what we do is, first of all, we start with a change of variable. Okay, so what we are going to do is this. So let's say u of xt is 0 to t integral over Rn phi of, okay, I am just doing a change of variable. Let's just write it and I will tell you why I can write it like this. Y of s f of x minus y t minus s dy ds. How am I getting this thing? See, here I have phi of x minus y t minus s f of x y s, right? You take y minus x minus y to be z and t minus s to be some r, right? Make the change of variable, you see that you are going to get phi of ys f of this ys. I just wrote it some variable, you can write it to be z r. Okay, that's not a point, so you can just do it like this. So that will be zr, and then this changes to x minus y t minus s dy ds. Okay, so this is the change of variable. Okay, now since f has a compact support, okay, so f is in C2 with compact support, that is there, right? Compact support. Okay, and you see capital phi. So the fundamental solution is smooth, right? Where is smooth? Near s is equals to t, right? Of course, that is positive. Okay, so we can compute this thing. See, ut of xt. Okay, we can compute ut of xt. What is it? Now I am doing the differentiation under the sign of integration. Yeah, what happens? First thing first, you can write the whole integral together, and this t will go inside, right? So it will become 0 to t integral of our Rn. Yes, phi of ys. This is essentially constant in our case, because we are essentially taking the derivative with respect to time. There, this nothing will change here, because this s is independent of t. Okay, I mean, of course it is less than t, but it's not dependent on t. That's all. Okay, in that sense. So now this becomes ft. So the derivative of f with respect to t times x minus y t minus s. Clear? dy ds. Okay, plus, if you remember the boundary terms, okay, plus the derivative with respect to the time variable, okay, which is 1, times integral over Rn. So essentially it is integral over Rn phi of y t f of x minus y 0 dy. Okay, let me again explain to you what am I doing. I am using integration under the sign of, so I am using differentiation under the sign of integration. Sign of integration. Okay, now see, one fundamental way here is this. See, why we did this change of variable. If you understand, I mean, let me recall again why we were doing this change of variable. Change of variable is required in order to take the derivative inside. Okay, so essentially what am I doing here? As I told you, phi has a singularity, right? Phi has a singularity, and you see this formula here, phi has a singularity when x equals to y. Yeah, this x and t is fixed, right? Yes. So let's say when and this y is varying in Rn. So at some point x is going to be y and t is going to be s, right? So let's say if that is the case, then you are looking at phi of 0 0. We know that phi as a fundamental solution has a singularity at 0 0. Yes. If you have a singularity, that differentiation under the sign of integration won't work here. So you can't take ut and you can't hope that ut, this time variable, will go inside. Okay, you can't do that. So that for this formula to hold, phi has to be independent of all such singularities. So what we did is we changed this variable and wrote it in such a way that we can do all of this. Okay, and that is why this is true. Now I hope this formula is fine. Yes, and what happens at the point 0 0, the derivative of 0 is 0, so that 0 point is not there. With respect to t, it is 1, so 1 times this whole function. So I just wrote that whole function. Okay, and of course it is evaluated for t, s equals to t, so that is why t minus t is 0. Okay, if you remember differentiation under the sign of integration, this term is there, right? You just take it inside, this term is there, del f del t. Okay, that term is there, but I mean this is the constant kind of with respect to t, this is essentially a constant, so I can take it out, and this is the boundary term. So essentially, if you remember the derivative term with respect to the this thing limit, so derivative of t is 1 times the whatever the function is evaluated at the point t equals to s. So t equals to s is 0, that is why it is 0, plus derivative of 0. Okay, derivative at the point 0 is 0, so essentially you do not have that term. So ut looks like this. Okay, so now if ut looks like this, also del to u del xi del xj. Okay, how does this look like at any point xt? That will look like 0 to t integral over Rn. Okay, capital phi of ys. Okay, del to f del xi del xj of at the point x minus y t minus s dy ds. This is for I j 1 to n. Okay, so what are we getting here? Let us just understand what are we getting here. See, in this case ut look like this, right? So if you replace ut by uxi, the same thing will happen here, except this derivative is with respect to 0t, here the derivative is with respect to Rn. Okay, so first thing first, 0 to t integral over Rn, that part is always there, and you just push the derivative inside, right? So that's I mean, in case of second derivative also the same thing has del to f del xi del xj it will be, right? Okay, now we will have a boundary term here. So the derivative in uxi, if you are going to take, that will be with respect to this variable, right? Integral over Rn, this variable. Okay, 0 to t will be there, but with respect to this variable. But you see, there is a trick here. What is happening here is this. So there will be a boundary term. Essentially, there will be a boundary term, right? Okay, but what is happening is this. After you have this boundary term, if you differentiate it twice, so uxi xj, again with respect to when you are differentiating, then this boundary term vanishes. Okay, so that is why there is no boundary term here. So please verify that. Please verify this. Clear? Okay, so please verify this thing. Now, so if this is the case, therefore what you have is u, okay, u xi xj, okay, u xi xj, okay, ut, let's say ut u xi xj, they are continuous, right? They are continuous. Why they are continuous? If I am asking you why they are continuous, can you tell me? Why they are continuous is because phi is a continuous function. Okay, I mean phi does not have a singularity in this part, right? Okay, so phi is a continuous function, and I mean f is C21, right? So twice differentiable with respect to a one variable and once differentiable with respect to t variable. Okay, so that is why ut, this whole thing is continuous, the whole function is continuous, and again u xi xj, that is also continuous. So they are continuous functions. Yeah, where in Rn cross 0 infinity. Clear? Okay. So if they are continuous, of course, what happens? Therefore, we can say that u is in C21 of Rn cross 0 infinity. Okay. I hope this is clear. Why? Because you see, u is twice differentiable with respect to x variable from here, and u is once responsible with respect to the t variable, and they are continuous functions. So that is why u is in C21 Rn cross 0 infinity. That's the definition, right? This is the definition. That's the definition. And I hope the continuity part is fine. Okay. This is continuous because f is given to be C2 with respect to x variable and C1 with respect to t variable. So ut and uxi xj, they are continuous. Clear? Okay, now I have to show the second part, part 2. Okay, for part 2, what we do is we calculate ut at xt minus x of uxt, right? I have to show this is equals to f of xt. So this is given by 0 to t integral over Rn. Okay, the fundamental solution evaluated at y comma s, and then I have del t. Okay, let me write it down and then I will explain to you. Minus phi x. Okay, and what do you have? You have okay, f of x minus y t minus s dy ds. Okay, that is there. So I have the boundary term also, right? I have this boundary term, integral over Rn phi of y t f of x minus y 0. Okay, so plus integral over Rn phi of y t f of x minus y. Okay, and 0, right? X minus y 0 we got, right? Phi of y t f of x minus y 0 and ty. Clear? So we have this stuff. I'm just writing this part. I'm just writing it together. That's all. Okay, nothing else. Okay. Now once I write it, see, now what am I going to do is I'm going to break it up into 3 parts because phi has a singularity at 0 0. Okay, if you remember. So I just want to break it up into epsilon t Rn. Okay, phi of c. Here I do not have to work with Rn. T, if I am just taking from epsilon in t, then for any x in Rn, the singularity here is gone, right? So phi of ys, phi does not have singularity in this interval, epsilon t between epsilon t and integral over Rn. Here there is no singularity of phi, right? Okay, I will do another change of variable here. Okay, so I will write it like this: minus del s minus delta y of f of x minus y, okay, t minus s dy ds. Clear? So that is there, and plus 0 to epsilon integral over Rn phi of ys. This part is there. Epsilon to t was done. From now 0 to epsilon has to be taken care of. This, let me write it like this: minus del s minus delta y, okay, f of x minus y t minus s dy ds plus okay, this part is there, plus integral over Rn. Let me write it and then I will explain. Yes, yt f of x minus y 0 dy. Okay, so this I am writing as I epsilon plus j epsilon plus ijk. So this all depends on epsilon. So I epsilon plus j epsilon plus k. Okay, now what I am going to do here is this. See, I am doing a change of variable here. So this t is getting changed to s. T minus s, let's say this is r, right? Yeah, now you just change this variable to s. That's what I'm going to do. So basically r variable del r, and that I'm writing it as s. That's all. And again similarly, this delta x is getting changed to delta z, let's say, and that z I'm just replacing. See, x minus y, let's just write it as z, and then this derivative is getting changed to delta y. delta z, and that z I am just writing it is just a variable, right? So I can write it like y. Do you understand what I'm trying to say? I'm just changing a variable here. That's what I'm going to do. Okay. And why this minus sign is coming? Because of the minus sign here. You see t to s is minus sign is there. So that is why del t is minus del s. It will be okay. You see t minus s is r essentially. Yeah. This is, I mean, I wrote it like this, but it is minus del r kind of thing. Okay. So I just want to change this variable t minus s to, so from t I just want to change it to s. So this is why this minus del s is there. And again here, if you think about it, why there are no change in the sign? Because one minus will come for one's derivative, but the next derivative another minus will come, so that will negate each other, and that is why the sign remains unchanged. Okay, and then you have f of x minus y t minus s. If you are not convinced with what is happening here, so I want you to do is, again, please check this part. Please check this. Okay, I told you what you need to do. Now you just do this part. Yeah. Now one small detail I want you to understand is this. Some parts I'm just leaving it out. Yeah, this is intentional. Some calculations. Yeah, so some calculations are intentionally left. Please, calculations are intentionally left. Why? Because you see, because the thing is, if you do some calculations yourself, you understand, you will become more fluent with what is happening here. So this change of variable formulas and the integration by parts formula. So the more you do it yourself, yeah, the more fluent you get. And that is why I did not explicitly write down every particular details. Yeah, but that is not very beneficial for you. You will just look at the video and it will go on. So what I want you to do is, I will give you all the required information of how to do it. What I want you to do is, please check it yourself. Take a paper and pen, just do it yourself and see if this works or not. Okay, so in this case you just have to look at del t minus delta x of f of x minus y t minus y. These you want to write it as minus del s minus del y f of x minus y t minus s. Okay, this is just a change of variable, but what I want you to do is, please check this part if this is true or not. Okay, right. So now once this is true, so what we have is this. Now let's just calculate one part. What is, first thing first, I have to show what? I epsilon plus j epsilon plus k, this has to tend towards f, right? This has to be f. So this calculation has to be done. Now let's look at this particular j epsilon first. Yeah, 0 to epsilon integral over r and phi of this particular thing. Okay, so mod j epsilon, this is 0 to epsilon integral over Rn. Okay, what do we have? Minus, where is it? One second. It is minus del s minus delta y, minus del s minus delta y of x minus y t minus s phi of ys. Okay, dy ds. Okay, so let's just take the modulus of that. So I want to make this as small as possible. Okay, so if I want to do something like this, can I mean, let me write it down and then I will explain. Then I want you to think about it. Why can we do this thing? So what am I doing is this: I'm taking the maximum of ft. Okay, I know that ft is bounded. Why? Because f is twice differentiable with respect to the t variable with compact support. With compact support, what does that mean? It means the set of all those x where fx is non-equals to 0, the closure of all that set is compact. Clear? So ft, f with respect to the t variable, that must have, so f with respect to t must be bounded, right? Must be bounded. Okay, and this bound we are just writing it to be the maximum of this thing. This is, I'm just writing it to be infinity. Okay, so it is bounded by L infinity, and then you also have another bound. Okay, so from here this minus del s of f, that I am just bounding it by ft, the L infinity of f. Okay, and there is another minus del y of f, so the twice derivative of f, this I am bounding it by d2 of f, and that is also L infinity. See, f is in C2, is twice differentiable with respect to the x variable with compact support. Okay, so delta y, the twice derivative of f with respect to y, that is also bounded, right? So d2f, that is bounded, so you just take the infinity norm, the maximum norm. Okay, this is there, and what is left out? Left is this 0 to epsilon integral over Rn. Okay, and capital phi of ys, y comma s, dy and d of s. Okay, so that is your left out part. I hope this is fine. See, integral of the whole thing is less than equal integral of 0 to epsilon 0 to integral 0 to Rn mod of this whole thing, right? Mod of this whole thing. Yeah, phi is positive, so mod of phi is basically phi. You just write it. So essentially I have mod of minus del s minus delta y of f of x minus y t minus s, something like this. Yeah, this mod is there. Now you see, this is what, this is basically the first derivative of f. So basically this is less than equal, I can take it to be del s of f. Okay, plus delta y of f, if you think of it like this. Yeah, and then this is just the derivative of f with respect to t variable. So ft, one variable, and it has a compact support, so this is bounded. Okay, what is the bound? It is the L infinity bound of ft, right? L infinity bound. So basically the maximum of ft in Rn. Okay, R, sorry. And here delta, so this I am just taking the max d2u. Okay, I am taking the maximum of d2u. So this delta y of f, this can be bounded by this. Okay, d2u, the L infinity norm of this. So L infinity norm, essentially here what I meant is the maximum. Okay, f. So whenever I am writing infinity, L infinity, I will say it means it is the maximum of f. Clear? That is fine on the whatever the domain we are working with. So I hope this calculation is clear. Delta y of f is getting dominated by d2 of f. Yes, and f of this is fs or f of t. I mean it's basically f with respect to the second variable. Okay, so and that is always bounded by the maximum norm of ft. Okay, so that is what I am doing. So you just take this thing and you have left out is 0 to epsilon integral over Rn phi of ys dy ds. Okay, now I hope you know what this what happens to this particular thing. Of course, this is the integral over Rn phi of ys. Yeah, what is it? Integral over Rn phi of ys, if you remember, it is 1, no? Only this part. Only this part. Okay, only this part is 1. Why? Because it's a fundamental solution. So integral of a fundamental solution, if you remember, since integral over Rn, okay, phi of ys ds dy, sorry, this is 1. Okay, for each t positive, hence what do you get from here? We get, so this is true, hence we get this is some constant, right? I can write it as some constant time integral over 1 0 to epsilon ds, so that is epsilon, so c times epsilon. Clear? I hope this is fine. Okay, so now again I have to evaluate what I epsilon is, mod I epsilon. What is I epsilon? Mod I epsilon is 0 epsilon to t. Okay, and then you have integral over Rn minus del s minus delta y of phi of ys. Okay, let's write it like this, and you have f, right? F of x minus y t minus s dy ds. Clear? Okay, now this particular thing, one sec, what do I have? I have this is I epsilon, right? if I remember, I epsilon is the same thing, right? This whole thing is I epsilon. Okay, I mean I just wrote phi here, but anyways it's I epsilon, epsilon to t integral over Rn. Yes. Okay, fine. This is I epsilon. Now what I am going to do is I am going to use integration by parts. Integration by parts on what? On t. Okay, integration by parts with respect to t. So the one variable integration by parts. Okay, what will happen here is this. Let's do that. So if you do integration by parts on this variable, what is going to happen? This minus sign is gone. The derivative will be pushed into that, and that the minus sign is gone. If you remember, see where is it? This is your I epsilon. See, j epsilon we calculated already. Mod j epsilon is small. I epsilon I want to calculate. What is I epsilon? I epsilon is this part, right? I epsilon is this part. It is phi of yt minus del s minus delta y of f x minus y t minus s dy dx. Okay. So when you do integration by parts, if you remember, the you push the derivative on the other part, and that is why this minus sign is no more. Okay. So it becomes, let me write it. It becomes epsilon to t integral over Rn, okay, and minus del s minus delta y, okay, capital phi of ys, okay, f of what will happen here is x minus y t minus s dy ds, right? So nothing changes here. It's just the derivative here, integration by parts. And what else is changing? One second, yeah, let me so this is there. I have the boundary terms now. So on the boundary, plus integral over Rn phi of y, s is, in this case the boundary term is epsilon f of x minus y t minus epsilon dy, right? And there is another boundary term corresponding to t. So that is minus integral over Rn phi of yt f of x minus y 0 dy. Okay, how am I getting all of this? I am getting all of this just by integration. So this is integration by parts, and what sort of integration by parts? This is just a one dimensional integration by parts. I am doing it on the t variable. Okay, if you just do the t integration by parts on the t variable, it looks like this, right? This changes sign to minus to plus, and then you have the boundary term. The boundary terms evaluated at boundary. So t evaluated s evaluated at t. Sorry, s evaluated at, where is it, t, and s evaluated at epsilon. So it goes on like this. Yeah. Okay, so once we have something like this, so this term I have seen somewhere, right? We have seen somewhere. Where did we saw this term? You see, this is k. You see, this term and this term is same, no? Okay, so this is k. So I epsilon, if you do not take just the modulus, let's just take the without the mod, let's say I epsilon, this is equals to this is equals to this, which by integration by parts is. So I epsilon plus k, this is k, right? So I epsilon plus k is essentially this part plus this part. Okay, because k is integral over Rn phi of yt f of x minus y 0 dy. See, so this is k. So I epsilon plus k should be this two term, right? Okay. So hence, therefore, these two terms can be written as integral over Rn. So I epsilon plus k, that I am writing it to be integral over Rn, capital phi of y epsilon f of x minus y t minus epsilon d of y. Okay, why I will write it like this? See, if I am taking the s variable from epsilon to t, what happens to this particular term? If you think about it carefully, phi is a fundamental solution. S is from epsilon to t. Okay, see, S is not touching 0 here. So what is happening is this particular term is becoming 0 because phi is a fundamental solution of the heat operator, right? So phi del S minus del Y of phi, that is going to be 0. So this particular term vanishes, right? This particular term vanishes. Okay, so I am only left out with this term, and this is what I just wrote here. Okay, so if I add all of this, therefore what happens is, therefore ut at any point xt minus delta of uxt, okay, is equals to limit epsilon tends to 0, okay, integral over Rn phi of y epsilon f of x minus y t minus epsilon dy. Okay, this is what we are going to get. This is what we are left out with. What is there remaining? Yeah, okay, j epsilon is c epsilon, right? Yeah, so that as epsilon tends to 0, c epsilon goes to 0. So I do not have to worry about it. All I need to do is I need to worry about I epsilon plus k, which is this. Yeah, okay, so see, let me again recall. Ut minus delta x of u is I epsilon plus j epsilon plus k. J epsilon is c epsilon, so this is very small. I epsilon plus k, this is what I need to make very small, okay, as epsilon tends to 0. So I epsilon plus k will be limit epsilon tends to 0 integral over Rn of this, because I epsilon plus k of this is this. Okay, now here I am going to write one thing which I want you to verify. As epsilon tends to 0, okay, this you need to verify. Okay, what I am going to do is I am going to write down what is the value of this thing. So the value of this, just take 1 second, just think about it, what happens to the value. Okay, pause the video, think about it, and then come back. So let's just think straight about this thing. If you are taking epsilon tends to 0 inside the integral, what is happening is, let's say this becomes phi of y0 f of x minus y t dy, right? That's what is going to happen. So this, if you integrate this thing, what is going to happen, and take the limit as epsilon tends to 0, this will actually go to f of xt. This is what we need to do. Okay, Rn and t positive. Okay, why this is coming? Okay, so sorry about the other part, you do not have to take it inside. So why this is coming, to look at why this is coming, what you do is you take the integral over in Rn phi of y epsilon f of x minus y t minus epsilon dy minus integral f of xt. Okay, this particular thing you have to make it small enough as epsilon tends to 0. So this thing you can write it as integral over Rn phi of y epsilon f of x minus y t minus epsilon minus phi of y epsilon f of xt, right, dy. I hope this is fine. Why I can write it? Because you see, essentially f of xt I can write it as times 1, which is integral of phi of y epsilon dy. Okay, and then I can take it inside, because x and t is independent of y and epsilon, so I can just take it inside and I can write it like this. Clear? This is the fundamental solution, right? So the integral of the fundamental solution is 1. I am just using that part. Now you see, this is becoming integral over Rn. Okay, phi of, I am doing a rough calculation here. I want you guys to actually do the whole calculation. Okay, f of x minus y t minus epsilon, proper calculation here. Please do it yourself. That is how you learn actually. Otherwise, you won't learn anything. Yeah, so phi of x minus xy f of x minus t minus epsilon minus f of xt dy. Now you see this particular thing, since f is continuous, okay, since f is continuous, you can make this thing as small as possible. So this will be less than some, let's say, delta. Okay, and then you will be left out with integral over Rn phi of y epsilon dy, which is 1. So that will be delta. Clear? So what is happening is, this particular integral as epsilon tends to 0 goes to f of t xt. Is this clear? I hope this is extremely clear right now. Okay. this calculation you just do it. Here what am I using? I am just using f is continuous, right? Continuous with respect to x and t. Okay, this is what I am going to use here. So this is fine. So the second part is done. Now for the third part, so for the third part, okay, what do we have? You see, one small detail we have to note here, that for small part, the third part is limit xt going to x, where is it? I am taking some point, right? X not 0 and x is in Rn and t positive, okay, and u of xt, this is 0. This we have to show for each x naught in Rn. This is what we need to show, right? Okay, so let us look at what we can find here. Yeah, so if we need to show this thing, what is our u of xt? U of xt, so this actually follows directly from the definition. You do not have too much. 0 to epsilon integral over Rn, capital phi of y is the fundamental solution of phi y is f of x minus y t minus s dy ds, right? This is what u of xt is. Now if you take the limit as xt goes to x naught 0, okay, so you have to take the limit at as xt goes to x naught 0 in this particular thing. So you see here you can do this, or you can take the u has a compact support, right? So u with respect to t, the maximum norm, L infinity norm with respect to t. See, I don't care about x anymore. I'm just taking the norm with respect to t. Okay, so that if I'm taking here the maximum between 0 and t, this norm, this is going to get, see, f has a compact support, right, with respect to t. So I can take that maximum. F has a compact, see, how do I put it here? See, f C21 with compact support. Okay, so what that means is f is 0 outside a compact set. So essentially what is happening here is a continuous function on a compact set attains a maxima, okay, and that maxima is with respect to both, because this is continuous with respect to x and t both, right? So you can take the maximum of f and you can push it outside, right? So that you can do. Let's say if you do that, then you have norm of f, L infinity, the maximum of f, okay, with respect to both variables, the maximum of f, and then you are left out with is 0 to t capital phi of ys, okay, dy ds. This is integral over Rn. Okay, now this particular thing is 1, so that will give you norm of f L infinity 1 0 to t ds, which is t. Okay, now once you have this thing, now you see as which actually tends to 0 as t tends to 0. You see here xt, t tends to 0 and x tends to x naught, u of xt must goes to 0, and the maximum of this thing goes to 0. So u of xt has to go to 0, right, as t tends to 0. Then you are done. Clear? So this is the end of this theorem. So if you want to put it together, okay, let me put the theorem properly. So of course, what is the formula then? You have formula. If you have this equation, ut minus Laplacian of u equals to f in Rn cross 0 infinity u is g on Rn cross t equals to 0. Okay, so here I am just changing this thing a little bit. Here I have f and here I have g. The initial condition, initially I was taking it to be 0 for our problem. Here I am taking it to be the most general one, f and g. Okay, and f is smooth with compact support. Smooth, of course, smooth means here C21, okay, with compact support, and G is continuous with respect to both variables, okay, continuous. Then let's write down what is the solution of this problem. So the solution of this problem is the solution of ut minus Laplacian of u equals to 0, u equals to g, okay, plus the solution of this problem ut minus Laplacian of u equals to f, and u equals to 0, okay. The solution of this is this. I can just break it up. Here, for this problem, we already know what is the solution. This problem, we already know what is the solution. If you add it up, you will get the original solution. So basically, with any solution u of xt, so let's say that's your 3, okay. So if u solves 1, 2, 3, then u of xt will look like this: integral over Rn. You know what is the formula for this. This is phi of x minus y t g of y dy plus integral over 0 to t, this formula, over Rn Duhamel, okay, phi of x minus y t minus s f of ys dy ds. Clear? Okay, so this is how you solve the inhomogeneous heat equation. Yes, so in next lecture, next week, what we are going to do is we are going to end the heat equation part with looking at the maximal principle, regularity of solution, okay, and of course how do you prove maximal principle and regularity? This is proved using a mean value theorem, okay, just as Laplacian, okay. But the thing is, this for heat thing, all mean value theorem, maximal principle and regularity are quite complicated as opposed to the Laplacian, okay. So we'll do that in next week video. Thank you.